Hey everyone, thank you so much for watching the Weaviate podcast. We have such an exciting podcast today. Etienne Dilocker is coming on the show again to talk about ANN benchmarks, approximate nearest neighbor benchmarks, and how you can find the optimal parameters for Weaviate's implementation of HNSW. So to take a quick step back before diving into it, at the high level idea with the Weaviate vector search engine, we're looking at how we can encode objects into vector representations. And then once we have these vector representations, you say, take your search query, similarly embed it into a vector space, and then you want to find the most similar vector. And one of the parts about this that makes it so interesting is once you talk about billions of vectors and like an absolutely enormous amount of vectors to do that similarity search with. And that's where this thing about approximate nearest neighbor benchmarks and algorithms like HNSW come into the picture, because they let you do this in a reasonable amount of time, find the most similar vector in an absolutely enormous collection of vectors. If you're talking about, like all the tweets on Twitter or just like, I'm sure that people out there can imagine absolutely enormous amounts of objects that you'd want to search through. So Etienne, thank you so much for coming back on the Weaviate podcast. And can you tell us about the ANN benchmarks?
Thanks for having me. It's been quite a while, I think, that I've been here. So very happy to be back. Yeah, the benchmarks, I think, is probably the most requested, well, feature is not a feature, I guess, in Weaviate, but one of the most requested topics overall from a multitude of directions. So new users might be worried, if I'm using Weaviate, can it handle the load that I would receive in production? Users evaluating different vector search engines might be wondering, okay, is this how quick or fast is it? And all that we had before was basically this like very vague claim that you can do a vector search in considerably less than 100 milliseconds. And that's sort of, if we look at the benchmarks that we just released, like I think maybe we were a bit too modest with that claim, because I think that's typically the search latencies are much better. But really benchmarking is like it's such a complex topic, and I think you can't put it in like a single statement of saying like, yes, you need to put some number somewhere on the website. Like you need to get people the impression, okay, speed and throughput is a concern for us. And I think that was the initial idea of just having something like that in our GitHub README. But yes, the benchmark show right now, it's such an interesting topic with different latencies and how like latency and throughput, the connection between those two. Then of course, dataset sizes, vector dimensions, like all of these things have an influence on what you can see. And yeah, I think it's super exciting because Weaviate is fast. I think we're sort of definitely in a very good state with our performance, and why not be super vocal about it? Why not show what we can do and not just make these like vague claims like, yes, it's fast, but we're not going to tell you how fast.
Mm-hmm. Mm-hmm. Okay. So can we maybe step through the complexity of what makes each different data set? So, say you have a billion paragraphs from Wikipedia that have been encoded compared to, I don't know, a billion images, or like what are the different things with respect to each of the data sets when you're trying to benchmark an approximate nearest neighbor search?
Yeah. So if we look at the current benchmarks, what we see is sort of, and what I would have assumed before is size is the most important factor. Like I would have assumed, sort of without any context, maybe that, let's say if you have something that's 100,000 objects and you have a million objects, you would think that the million object ones is considerably slower. And if you brute force this, which has basically O of n complexity, like linear complexity, that would absolutely be true. Like a brute force search through a million objects would be roughly 10 times as slow as one through 100,000 objects. But of course, we're using ANN indices, like in our case, HNSW, and we've talked at least twice, I think, once initially and once also with Yuri on the show. We've talked about HNSW, and the whole point of like this complex graph structure that HNSW is, the whole point of it is really that we don't have that linear kind of latency increase or throughput decrease, however you want to see it. And it should have been really obvious, saying that now, it should have been really obvious that dataset size isn't the biggest factor, but it's still, it's nice to see it. And it's in a sense, it shouldn't be surprising, but it still kind of is. And it's nice to see that. So that is, I think, a very interesting learning, also when applying this to different data sets. when users in the community tell us something about their data set, I think the first thing that they would mention is how many objects it has. And it's actually for performance, it might not be that relevant. It might be relevant for like resource planning and for cost estimates and these kind of things. But for performance, what we see, you can generally get the highest throughput. Two things have the biggest impact. One is the vector dimensionality. And I think this also relates a bit to your question about, let's say these are paragraphs from Wikipedia, or maybe these are images. Depending on the model used, different models use different dimensionality. And traditionally, I'm not sure if this is true anymore, but traditionally we would see that like text-based models have rather few dimensions. So maybe like 384 on something like sentence transformers. And image-based ones would have very high dimensionality, so 1024 dimensions, for example. And this would actually be the biggest impact that you could have on performance. And if we were diving a bit into how HNSW works and what's happening, is the approximate part basically tells you the index does something smart, so to speak, that you don't have to evaluate the entire index. It's a neighborhood graph. So by using this ANN model that HNSW has, it basically tells you here is a smart way to only evaluate, let's say, 5% of the index, because these 5% are close to your search query. And what sort of if we do this, we can kind of see why it doesn't matter so much if we're evaluating out of 100,000 objects or out of 1 million objects, because this 5%, of course, is a made-up number. Like it could be that in 1 million objects, suddenly we're only evaluating maybe 0.5%. However, the dimensionality of the vector is something like, if you've narrowed this down to, I'm making this up, let's say 100,000 vector comparisons, then you really see that the cost of doing 100,000 vector comparisons with 1024 dimensions is higher than doing it with 384. That said, I'm not sure if this sort of text is low dimensional and image is high dimensional. That's still true, because, for example, we're seeing clip, and in clip, it's the same vector space. So it seems to be very possible to compress that image information in a relatively low dimensional vector space. But I think it is something to think about just in general. Like if users are using out of the box models, then it's something to think about. Like, do I really need the one that has such high dimensionality? Could I maybe achieve the same thing with lower dimensionality? And same thing for if users are training their own models. Just think about the dimensionality. Like, do you really need maybe even 384, which seems to be like the sweet spot right now for text? Like, how much performance drop would you have if you cut that in half? Because the sort of benefits that you would get from an engineering perspective is half the memory, potentially half, it's not entirely linear, but potentially half the latency, like double the throughput. Of course, it's not linear in that aspect, but still you're going to get better throughput and better latency. So there's maybe a long answer to your question about different data sets. Like, really think about the dimensionality of your data set, and if you actually need it, or if you can maybe get a free speed up by reducing it.
Yeah, quickly, the idea of like how much can you compress into the vectors, it kind of reminds me of arguments around like, is intelligence compression, is being able to find the minimum description length of a program, is that the ultimate way of having intelligence? And yeah, that 384 dimension thing is so interesting. And so quickly, I did later in the podcast, I want to go a little more into binary passage retrieval. And I remember our podcast with Yuri Malkov and hearing about product quantization and starting to get a taste of that. And I want to quickly bring up again locality sensitive hashing and kind of how the problems with that. I guess it's not, because it's not learnable, is what I had taken away from Yuri, and maybe we could rehash that out a little bit on the podcast a little more, and then that maybe knowledge distillation to try to compress that. But kind of what I wanted to step back into is, so I'm a Weaviate user, and I'm coming to these benchmarks. So is it the dimensionality of the vectors again? So it sounds like the approximate nearest neighbor data structure is like, HNSW. And I really enjoyed, Eric Bernardson has a blog post series on explaining how Annoy works. And I highly recommend that to listeners who are, who are still getting caught up, as a way of understanding how the data structures divide the space. But so for a new Weaviate user coming to the new benchmarks webpage, is the dimensionality of the vectors, is that the key thing that they should look at to compare the benchmarks with their data set, or is there more to it than that?
Yes and no. So I think it's one of the learnings that I did. But I think the great thing about this benchmark page is it's it tends to be it's basically just information, and you can interpret in whatever way you want. And that's also why we use different data sets in the benchmark, so that you could pick the one that represents your use case closest. And that gives you, I mean, that can help you in different stages. Basically, it could be prior to using Weaviate to know what you could expect from Weaviate, but it could even be helpful in like a debugging scenario. Let's say you're using Weaviate and you're not getting the kind of performance that you would expect. By picking the data set that's closest to yours from the benchmark list, you could say, okay, like they were using this specific machine, they were using this many objects with this many vector dimensions, and they were getting, I don't know, I'm making this up, 5,000 queries per second throughput. I'm only getting 500. Then you have a very good indication that somewhere in that setup something is going wrong. And then, of course, the super interesting question is like, where is it going wrong? But I think debugging something is much easier if you know that you can expect more from it than if you're not sure. Like if you're saying like, this kind of like of the gut feeling, it's not as fast as it could be, but what is reasonable? And I think that is one of the questions that we also really wanted to answer with those benchmarks. Given these things, so two questions basically. Given these parameters, this is what you can expect. And then the second question is by comparing the different data sets to one another, changing these kind of parameters, what would change? And there, yeah, as I said before, one of the biggest learnings for me was that the vector dimensionality is a much more impactful than the data set size.
Mm-hmm. Would it be useful to maybe look at like a histogram of distances between, maybe you sample 5 queries and then you plot the histogram where, say, it's like a Gaussian looking thing of, you know, what the average distances are to the data set? Would that kind of thing impact the HNSW parameters?
Yes, you are raising something super interesting, because I think, I'm not sure if you're referring to that, but it matches perfectly that Twitter thread that we saw from Niels Reimers about sort of distribution of vector of vector points in the space. And he was doing that in the context of using random vectors. And if you use random vectors, basically by definition, they'll be evenly distributed. There's like there's no reason that there should be clusters, or there's no reason that objects are relatively far from one another. So you see that distribution curve where basically everything is close. And the problem in a neighborhood graph is, I think we initially talked about this when we talked about HNSW. Like it's based on that fact that if you, let's say, want to make a connection from someone in Florida, USA to Frankfurt, Germany, then in the best case, you might just only have to know one person, but that person knows someone there. So, and this is, I think, the more common example is you're just 5 or 6 hops, or any person on Earth is 5 or 6 connections away from knowing Barack Obama or any other famous person in the world. And that only holds true if some of those distances are actually large. Like if let's say I know my neighbor, and my neighbor, I mean physical neighbor, and my neighbor knows someone else in the same city, and they know someone else in the same city, then I can do 10 hops, and I'm not anywhere closer from Frankfurt to Florida. So it kind of depends on that distribution of objects, of having sort of long enough edges, so to speak, because it's a graph. And that is the problem, that if you use random vectors, all distances are going to be equal. So how do you sort of move in the right direction where it's closest to you, but still far enough that you're actually jumping enough distance? And there, the super interesting learning is that if you use an actual data set, you kind of get that naturally. Like you're not engineering your data set to be sort of, I don't know, to have clusters and have large distances between clusters. It's just something that happens. Like whatever data set you take, if it's images, there's bound to be some clustering. If it's text, there's bound to be some clustering. So simply by using, like, in a sense, it's simpler than random, because you feel like maybe I need to engineer this in a specific way where the distances are under control. But ironically, just not doing that and just using actual data that somehow has a meaning on it gives you that perfect distribution that works so well with these ANN indices. by the way, also other ones like not just HNSW, I think is a famous example one, but if we think of for example, IVF, so the inverted file one, same idea basically. You start partitioning your data set into clusters, and then ideally, if your search query can be answered by a single cluster, you can skip the others. But exactly the same problem here. Like if you think of a two-dimensional space where points are completely evenly distributed, so you have like almost like a checkerboard pattern or something where the points are basically where the lines intersect. How do you cluster that? Like, is it viable to put that into one cluster that matches everything? Well, yes, but then you don't have the benefits of cluster. If you do 4 clusters, where do you draw the lines? Like every combination is basically equally as good. Whereas if these natural, like if you have this natural clustering, that's where these algorithms really benefit from. And yeah, that was interesting to also see that. Like you can, if you run with random vectors as opposed to like keep all the data the same as on an actual data set and basically try to copy that with random vectors, you can actually get the same kind of speed and throughput, but at very, very bad recall. And then just using the actual, because, and that's specific to HNSW, because HNSW at some point, it just stops the search when it thinks it's covered it well enough. And the fact is basically that well enough is just way, way worse. So I think something might be making this up, but on like 1 million objects of 120 AD, I think the difference that we could see is something like 20% recall with the same parameters, where you would get 97% recall with an actual data set.
Interesting. So to recover that, would, instead of random vectors, where I guess like the random prior is that it's going to be normally distributed, evenly spaced out, if you had algorithmically generated vectors but the randomness came from like a Gaussian prior or bimodal Gaussian prior, or I'm now going to reveal that I don't remember too many probability distributions, but I think like Poisson, there's like other distributions, right? Like, would that kind of way of algorithmically generating vectors recover the properties of real world data sets?
I think yes. Like I don't know why someone would go through that effort, but I think, like, assuming that there is a way that you could randomly generate data, that maybe even through training something that is trained to reproduce random data that sort of matches the distribution of something that exists, I think you could get there. But in the context of benchmarking, I think it's much easier to just use a standard data set, basically.
Mm-hmm. Yeah, and I'd really like to talk a little more about clustering. I think so. Clustering is the key thing here, right? Like the representations of these vectors are clustered, and so the algorithms exploit cluster structure in order to facilitate faster search. And clustering is also kind of, I'd read an interesting paper that's something like learning to classify without labels, where you basically assign semantic categories to clusters and you use that to classify. Do you see that as, and I know also Weaviate has a zero-shot classification built into it as well. How do you see that like idea of, like maybe to provide a little more context is I'm looking into this idea of doing the Twitter analytics with Weaviate. And so what I'm trying to do is combine like the usual descriptive statistics where you look at basically segmenting, where you kind of try to like look at the view count and the engagement rate, and you try to look at the way that these two symbolic properties are distributed. And now I'm trying to add this semantic component where you can segment by the semantic clusters to do that kind of segmenting that data scientists kind of do. So maybe this question, I hope it isn't too broad, but how do you think about that idea of clustering to form semantic categories, and how that might differ from kind of the school of thought around symbolically labeling things and then fitting classifiers to them to form categories?
Yeah. I think it sounds like you're pitching a new custom module for Weaviate. So that's real good. Yes, and I think the only step really that we need, because if we naturally have those clusters and we can discover those clusters basically have a centroid point or a centroid vector that represents the cluster. So really the only thing that we need to do is jump from that centroid to something that can sort of classify it in a way. So if we think of the contextionary module that we have, which is a very primitive kind of, it's not a deep learning model, or maybe there's deep learning involved in the training, but in the way that we apply it, it's essentially just a lookup list for words and vectors. And by having such a simple mechanism, you can easily do it the other way around. If you have like, this might be a viable option. If you already have some data, just calculate the centroid vector and just ask the contextionary, assuming it's in the same vector space, of course, ask the contextionary, like, what are the nearest words that you know of in that space? And then if we, and that could be something like the label or something such more complex. And then if we think of deep learning models, and you probably know this way better than I do, but I could imagine that that's not too different from generator models, right? Like if a I don't know, you have something like a text summarizer, I could imagine that you could tweak that in a way where you just give it an input vector and tell it to I don't know, create a label or something. So basically text to vec in the opposite way, like vec to text. That should be doable, right?
Mm-hmm. And yeah, I'm pretty obsessed with this idea of prompting and how the T5 text-to-text transfer transformer shows that you can kind of unify all the tasks into language modeling. And so yeah, that idea of classifying it like zero shot by having the kind of prompting interface. And so I've been really curious about recommendation and that kind of thing. And maybe, do you think that recommendation could be also put into that language modeling framework where the prompt is, say I'm recommending movies, and so I would say the user is Etienne Dilocker. He likes dogs and wine, say, and you use that as the input representation, like the prompt, and then it like, well, so, and then the prompt, and then it goes like, so what movies do you think Etienne? And like Etienne liked Iron Man, like the history of how they do the recommendation, and then you just turn it into a language modeling problem where you generate the kind of next movie. Do you think that kind of thing would work, or it's probably too grandiose of a way of formatting the task?
No, that I think that could absolutely work, because what I know, or I sort of have to build this based on what I know, is that we see users using vector search as the first step of their recommendation pipeline, where they use vector search basically just to generate candidates, and then have some other logic to sort of base, like let's say, staying with the movie example, we're taking the last movies that I've watched, and then we're now looking for something that's in some way related. And related, I think, doesn't necessarily have to mean like, because this was a comedy, this has to be a comedy, but could be anything. And then sort of to have, these other inputs in there as well. I think I could absolutely see that sort of as something that you would either do through re-ranking, which is basically what our users are already doing by applying their ML logic on something that's originally a vector search, or maybe even by building this into the model itself. Basically, that the similarity search wouldn't necessarily return something that's similar, but would return something that maybe is similar in the sense of the user likes this, therefore they also like this. So where the vector space would maybe not so much represent the in the case of movies, like the movies, but maybe the users, where you then search for similar users or make these kind of jumps in that space.
Yeah, one paper I really liked is it's doc to query, and what they do is they run a model that predicts a question given a document. So it takes the document as input, generates a question, and then what it will put into the vector database is that pair of generated question and then the document. So it's kind of like a way of adapting it to question answering, because then you kind of have that like lexical similarity sort of with the style of asking a question. So yeah, I'm curious about that idea of adding prompts to queries, maybe to have it go into the space, and then maybe the particular application recommendation. But maybe to step out a little bit, I'm very curious about re-ranking. It looks like there's quite a few ways to think about re-ranking. And I'd like to start with, I know you implemented binary passage retrieval and really got into the details of that. I'd like to talk about that idea of maybe a coarse-grained stage 1 retrieval and then a more fine-grained stage 2 retrieval, and whether just with binary passage retrieval as the coarse-grained step, and then maybe just retaining the floating point values of, say, the top 5,000 retrieved candidates, and then having maybe like a brute force search within that second stage or some other thing. How do you think about these like multi-stage refining pipelines maybe?
Yeah. I think there's almost no way around them, because if you, so BPR, I think is, or the motivation behind BPR is basically performance and or sort of memory costs. So by originally searching through these compressed vectors, the goal is then to sort of have a smaller vector space and therefore smaller resource requirements. And then the re-ranking is only to get back to the original quality. But I think re-ranking has much more potential than just sort of sort of improving upon the loss of compression by producing something that's actually better. And like in the simplest sense, could be, for example, re-ranking based on keyword matching. So let's say you have the typical problem here of these pre-trained, for example, sentence transformer models is they are great on general purpose data, but the closer that you move to domain-specific data that they haven't been trained on, the worse they become. One way, of course, is to fine-tune them, but that's maybe not always an option. So, for example, if someone who's not from the ML space just wants an out-of-the-box solution that works okay-ish, then fine-tuning may not be an option because they've maybe never trained the model before and don't even want to get into that. And then let's say we have a case where we have a model that's generally quite okay. So let's say e-commerce, you search for a brand name and like winter apparel or something. And then it might be really good to make that connection from like winter apparel to, let's say, a jacket. But it's very bad at matching that to the brand name that was actually in there. So let's say you have Nike, Adidas, whatever in the search query, and then the model almost ignores that. So if the original candidate selection was good enough, then you could even re-rank this with something super primitive, such as BM25, which is basically just keyword matching. The problem here is, of course, if those matches weren't in there. Like if you can only ever re-rank basically what was already matched. So I think you need to be in a situation where the matches were good enough, but you maybe don't necessarily agree with the order. So like the, I don't know, top 200 ones are good, but you can really only recommend one out of those top 200 and you don't agree with the order within those top 200. And I think that's where re-ranking really shines.
Yeah, that's a really interesting flow of you have, say, the Wikipedia trained sentence transformer that can do like pretty, semantic similarity, cover a pretty massive distribution of text. And then once you get like the top 5,000, now you have the BM25 lexical style re-ranking, which what are the, because you want the exact term. And we talk about things like serendipitous discovery with respect to how people really interpret what's returned from a vector search engine and that kind of fuzzy distance. And that makes a lot of sense to me. And I'm also thinking about this idea of, say, pairwise classifiers and personalization. So we have, Etienne and Connor, and we're recommending movies. Would we have, we could re-rank this list by having some kind of labeled data set where we have pairs of movies. Etienne chooses movie A, then, we show Etienne movie C and E, Etienne chooses movie E, and then you use the pairwise thing to do the re-ranking. What do you think about that kind of approach to it?
Yeah, just I think the great way of re-ranking is that you can re-rank on anything really. Like if you have the initial list, anything basically that you can train something on, I think that's you can re-rank based on it. And maybe even to go outside of the space of machine learning itself, it could also just be some simple business logic. Let's say to sort of stick with the e-commerce example again, it might be that the shop is not necessarily interested in presenting the best match, but maybe in what they have the highest margin on. So it could be like that you put in these completely different, where we tell the out of the box, trained on Wikipedia data, like how is that model supposed to know that if they sell, let's say, Nike over Adidas, that they get a higher margin? But through re-ranking, I think you can really sort of put potentially, and whether this could be something as simple as if brand equals Nike, then +2 or something, or it could be like this complex model that's basically learned that if we sell Nike shoes in summer, then I don't know, our bottom line sort of improves, and that deviates a bit from your original question about pairwise ranking, but I think it's sort of what I want to convey is basically that anything goes.
Yeah, that's one of my favorite things about the vector search engine and Weaviate and studying Weaviate is the way that it can plug in symbolic algorithms with the neural retrieval. You have like symbolic ordering of how you then process the neural algorithm. And I love the playing of those two algorithms. And I think that's a really nice transition to what I wanted to talk to you about next. And, I recently had the opportunity, it was such a great time to attend the Knowledge Graph conference in New York with Laura. And see Laura's presentation on question answering, watch the room reacting to it, and it was really just such an incredible experience to see. And I really wanted to get your perspective on semantic web ontologies and understand how you think about these kind of things.
Yeah. So for me, I think this ties very well into the previous question, because like I see myself and my role a bit more in enabling the platform to then build these kind of use cases on top. So I don't think I'm an expert on knowledge graphs, but I might well be an expert on sort of providing the platform that you need to search through knowledge graphs. And yeah, I almost like that I don't have a good answer on the knowledge graph. Like you were part of the knowledge graph conference. You can tell me probably a lot about what is going on there, and I wouldn't even know. So I really like this, that it's, in a sense, Weaviate is so general purpose, so to speak. Like it's good at specific things, but still it's so general purpose that there's such a wide variety of like, yeah, from e-commerce to knowledge graph to movie recommendation. It's like, almost feels like the base of anything that you want to do in that space in the future.
Yeah, the class property design of Weaviate, where you can have these cross references between different classes. I'm starting to see how kind of like I perceive as elegant this abstraction is. I've seen like in our Weaviate Slack, someone had asked, how do I encode multiple languages? And Bob had responded, you could have a cross reference that links between the two languages as different classes. So I see that as a way to do, say, like multimodal image text, where you can have a cross reference to the other image, as well as this kind of ontology relation style where you say Connor is an employee of SeMI Technologies, is a business category vector search engine, like this kind of way of relation style. I think it's such an interesting thing. And then within each thing, you have these HNSW index structures within each class. So kind of like a quick clarifying question. So each class gets a approximate nearest neighbor data structure?
Correct. So the class is essentially like a namespace, or in the MySQL world, I think it's called databases. So where you have the whole database and you have individual databases. In Kubernetes, you would call it a namespace. So yeah, it's really the unit of isolation, basically.
Mm. So in one Weaviate instance, I could have, say, 3 HNSW indexes for the 3. Very cool.
Yes,
yeah, I think that's such an interesting part of it. And doing that kind of linking is really just one of the topics that is interesting me the most right now, definitely. And so maybe transitioning from the knowledge graph thing, and it's a bit jumping to a different topic, but so I wanted to ask about Weaviate custom modules, and if you could tell me a bit more about what it takes to extend one of the modules it seems like to me, if you want to say point to another, say, Hugging Face model path, you look at this like Python inference container. And I'm sorry, this question is kind of going around the place for our listeners, but maybe could you start with the understanding of Weaviate core and then like the Python inference containers?
Yes, absolutely. So Weaviate core in itself is a vector search engine. Basically, that means Weaviate does not understand anything but vectors and the objects that are attached to that vector. So often called metadata. I don't think we use that term, but it's very commonly used in the space. And of course, the whole object has a lot of complexity around it as well, with different data types. But essentially, the idea is that if you use Weaviate without any modules, Weaviate doesn't actually understand how to go from, let's say, text or image or any of those to vector. So if you use, for example, the near text in the API, you need to provide a module that basically does that translation. And one of the ways to use sort of a custom module, I think there are several levels sort of abstraction, or not maybe of abstraction, but of how deep in the stack do you want to go to create such a custom module. And as you already mentioned, starting with something existing can be super helpful. So for example, starting with we have the text-to-vec transformers module, and the point of that is basically this text-to-vec translation. So if you use this, all your objects that you import will be turned into, or will be vectorized, and the vector will be stored and indexed in the HNSW index. And the same is true at query time. So essentially, you can use Weaviate like a traditional search engine that supports text now. And of course, if you add an image module, it would be the same for image. So what that does, this module, is basically it extends Weaviate a tiny bit in a sense that it tells Weaviate, okay, now you will have a near text search operator, for example, because that's not part of, like, it's not that it's there in Weaviate core, but you can't use it, and now you need a module. It's just not there if there's no module. So this is sort of, and this is, I think, the extreme strength of that module system, that any new module could extend Weaviate in any way that we can't even imagine yet. And basically, yeah, you have this small piece of code in Weaviate itself, I guess, or closely running in Weaviate core, like it would from an engineering perspective, it would run as part of the same, like it would be a plugin that runs as part of the same process that Weaviate is. But then what that small piece of code can do is it can just send requests to something else. So here, this you mentioned the PyTorch inference container. Here, the idea is that a vector search engine has very, very different requirements from a resource and infrastructure perspective than, let's say, model inference. So the idea is that you split that out, sort of basically a microservice pattern. We split that out, and Weaviate, that does vector search comparison, which is most likely CPU bound, makes that network request to something else, which could, for example, run a model that's running on a GPU. Like these deep learning models, they tend to run very well on GPU, or there are also efforts to optimize them for different CPUs, but typically they run well on GPUs. So what you can do in that journey basically is, I think, 3 different parts to come up with a custom module. The first one would be, you take that inference container, that existing inference container that's built for transformer models, and you simply run it with a different model. So you could, let's say, download a model from Hugging Face, or you could have a locally compiled model. And as long as, and there are instructions how to do that in our documentation, as long as you get that new model inside of that container, you can reuse everything there. So in a sense, you could call this a custom module already, because it's something that wasn't there out of the box. You have now your, I don't know, fine-tuned model there. The second step is, you could say, the use case that I want to do is the same. I still need text to vec, but my model architecture is so different that I can't use the PyTorch container anymore. So for example, something completely new comes up, some new way of running a model, or it could be maybe not something new. It could be like Onyx or these sort of optimized compiled models that simply have a different architecture. What you can do in this case is say, I want to keep the part in Weaviate that controls the API, because my API is still going to be from text to vec, and I'm still using this near text near text search parameter basically. But how that's done, like the implementation, is completely replaced. And that would be sort of at the microservice level, where we're now saying we're simply replacing one microservice with another. And the only thing that needs to match is the API. As long as this API contract between Weaviate and the inference container is upheld, you can entirely replace it. You can do whatever you want. And I think this is more commonly something that people would start calling a custom module. But then there's a third option. So the third option is, what if we want to, for example, support a completely different media type? So let me think of one that we currently don't support. So let's say audio to vec. You want to start with audio to vec. That means you can't just replace the inference container that does text to vec, because of course the interface is, it takes text, and you now need a completely new API. You need to get sort of that audio part in it. I don't know, let's say for the sake of argument, you would just upload an MP3 file or something like that. And for that, you actually need to change the entire chain of the module. So basically, you need to change that part that extends the Weaviate API, so basically the plugin that runs in the same process. And then most likely, you would still run with some sort of an inference container. But that's actually not part of the module system. That's basically just a convention that the existing modules use. So you could, if it's not needed, you could run it inside the plugin directly and never have that split out microservice. Or you could say, it's probably a bad example for audio to vec, but for the sake of argument, let's say you need 3 steps and you need 3 different models. Let's say one, I don't know, one cleans the audio, the next one sort of cuts it into chunks, and then the third service actually vectorizes. So made up pipeline. But if that was your pipeline, you could spin up 3 containers, for example. And that, I think, is really the strength of the module system, that in the end, it's just a tiny piece of plugin code that extends the Weaviate API and then can do whatever it wants with that API. And that gives you these 3 levels, basically, of hooking into it and integrating something custom into it.
Yeah, that's super. I think the extensibility of that is super interesting. And I do think there's a bit to unpack there. And I'm really impressed with the Google Summer of Code initiative and the Weaviate projects that I'm seeing, and the titles of them sound kind of like this thing, like the idea of, maybe just adding a new Hugging Face module and understanding how to do it, or how to add audio to Vec. But if you could maybe take me through, let's say I want to add a new Tokenizer and I want to add a new Hugging Face module. Would I need to pull request text to Vec transformers, add in my 2 things, and then push it back to the main GitHub thing?
Yeah. Essentially, if you wanted, so the sort of pushing it back point would mean that you would release it for everyone. That's one option. Another option would also be that you have something private that you don't want to release back to the community. So in either way, I think you would. So for the first one where you want to release it, you would definitely have to fork it, issue a pull request, and when the pull request is merged, then it could be available for everyone. If you do it privately, there is sort of a smoother process for this, where you do this at the Docker level, where basically when you do a Docker build, I think there's one environment variable where you can put in the Hugging Face a URL string. So the Hugging Face bundles up the models with their tokenizer and everything, like under one string, right? That looks a bit like a GitHub repo and organization and repo. And I think we have these Docker files where you just put in exactly that string, and if it exists and if it's accessible, then it will download it and sort of build that in your container. So yeah, if you don't plan on publishing it, if you only plan on using it, you can even take that step. But if you want to publish it, then the pull request would be the right.
Yeah, that's so interesting for me, trying to get deeper into Weaviate and trying to really understand it. And for me, I'm a little scared of things like Docker files and Go, and I've been trying to just roll up my sleeves and get into the details of it. But it does feel pretty accessible. The Docker containers, I think there's a bit of a learning curve for it if you're totally nothing, but I do think that it's pretty accessible. And so great. I think that was a really great recap of a bunch of different topics that I wanted to ask you about. And maybe any closing thoughts on the approximate nearest neighbor benchmarks and changes to the website, and helping people understand how to configure their HNSW through the use of these benchmarks?
I would say, first of all, check the benchmarks. That's the most interesting thing. Like, look at them, be convinced that Weaviate can match your performance goals. And then share the benchmarks. That's, of course, also super interesting for us to spread the words. And everything in the benchmark. Oh, yeah, that is something that I actually haven't mentioned yet. Everything in there is open source. Our intention is that you can reproduce. Like, we're very transparent about every single step that we do in there. We ran those on a single machine. We ran Weaviate on a single machine in GCP. That was, I think, a C2 standard 30 or something. It's in the article. And we ran the benchmark script on a separate machine, which was just sort of best practice for benchmarking. Like, you don't want your benchmark script and your server competing for the same resource. So we split that out onto 2 different machines. And the repository to import everything, to run all the scripts, to compile everything down to the graphs that we're showing in the article. All of it is open source. So if you think we made a mistake, or if you think we in either direction, basically, if you think we're doing something that shows numbers that are too good, or we're not optimizing something, it's open source. Everyone can contribute, and I think that would be my key message there.
Yeah, super cool. It seems so exciting, developing all the benchmarks and having all the research and the science, the reproducibility that comes out of having open source reproducible benchmarks. So thank you so much, Eddie. And I really enjoyed this Weaviate podcast. I'm learning so much about Weaviate. I really love this topic and things we discussed, like the class property referencing. I think all of this is just so interesting.
Awesome. Thank you. Thanks for having me. Time went by very quickly. It was a nice one. Thank you.